Good. So what I want to do today is basically come to the unsteady state heat diffusion equation. We had so far looked at the steady state. And now we want to add this time dependence to the equation and then look into the steady state diffusion. I have a few slides I can show you to just motivate why heat and heat transfer is actually it's a very interesting phenomena and studied quite a bit actually. And then see how that actually comes to geophysical problems, where we also see heat diffusion. And then I want to quickly maybe add a short note about basis functions that we saw in the finite element method. And also on unstructured meshes. That's often a topic that you will hear about when you look into finite element meshing. And so let me start with the slide about the heat transfer equation, just to motivate a little bit what we want to do today. So we lost Sishu. Let's see if she logs in back. And in case we just have this recorded as well. So you can look this up later as well. So let me quickly show you the slides. So we still stay with the finite element method. Now our interest is basically on heat transfer as a time-dependent phenomena. If we look at what we did so far, we looked at the steady state heat diffusion equation. There is no time dependence. And for example, here, it's still showing you an example for the steady state heat transfer, where you have, for example, cooling at the casing and heating at different parts, basically, in engineering. So you might think of having something that has contact with the cooling pipe or cooling surface, and on other sides you have constant heating, and then you're interested in the steady state. Let me see if I can add this issue into the steady state temperature field in your material, for example. How can I? Maybe she just dropped again. Maybe the connection has to come back first. Good. So that's in engineering is still important to look at the steady state, for example. But then when it comes to the heat transfer, so when you add the time dependence of it, it's a phenomena that is studied on all different scales. And here, this is just one example to highlight that you can go to the very small scale, so nanoscale, and look at heat transfer, for example, how that how heat would evolve, for example, if you have these nano stem cells. So really on the smallest scales. But then you can almost look at all different scales, even up to the global scales that we have in geophysics. where heat transfer is an important phenomena. So it's a very interesting physical phenomena that you can study. It's also interesting, for example, when you look at biology. In biological tissues, you're interested in the heat transfer. Let me see if I can add that. Good, let's see if you're back. So these are just a few slides about the motivation of heat transfer. And so you can look at it from an engineering perspective, but also from a medical perspective. So if you look at heat transfer in biological tissues, the aorta, heart, vessels, that's also applications where you are interested in heat transfer. And then when it comes to geophysics, the typical example in geophysics is the half space cooling, so the plate cooling. And you have these hot mantle material basically at the ocean ridges, and then it cools off. And we are interested in, for example, looking at how the plate thickens through heat transfer, basically how the cooling leads to a thickening of the plate, which is governed by the time-dependent heat transfer equation. So this is then the half-space cooling model that is often used to model this thickening of the plate. And here is such an example where we look at this thickening of the Pacific plate, and you see the age of the plate versus the temperature profile, basically. And so the age of the plate is related to the distance to the mid-ocean ridge. So think of, on the left side you have the mid-ocean ridge, and then you move away from the ridge, and the plate thickens with that. So it thickens with age. And the green lines, if you look in the figures, those are isotherms. So it's where the temperature reaches 1,000 degrees or 1,200 degrees. And that can be computed by this half-space cooling model. And that's what we're going to do for the homework. So we're going to plot basically the solution to the half-space cooling model. Now the observation is the one in red and blue that comes from seismic tomography, trying to convert into temperature. And what you see is that the thickening of the plate, it pretty much follows this half-space cooling model until the age to around 70 million years, 80 million years, where you then see that the actual isotherm, it starts deviating from what the half-space cooling model will predict. So there is still a debate why that is happening. And so there are hypotheses that at that age of the plate, you start having a new thermal effect, a new boundary effect that comes into play, and that leads to these differences to the half-space cooling model that we see. So you see that at higher ages, like 100 million years, for example, the thickness of the plate is much thinner than what would be predicted by the half-space cooling. So this might be an indication that we do have a new regime in this thermal boundary layer that leads to this thinning then basically of the plate at that age. And so there's still debate about this, what actually happens to the plate thickening, for example, for the Pacific plate. And the other debate is if, in terms of climate change, we are interested in, for example, how strong the oceans heat up. So the temperature of the oceans. And so obviously it also depends on how much heat comes from the bottom. So through these oceanic ridges, for example, how much heat is transferred into the ocean and how much of it leads to a warming of the oceans, for example. And this is not very well understood, actually. So this heat transfer into the ocean, there's a lot of unknowns and a lot of uncertainty involved in that assumptions. So again, the heat transfer problem is very important, actually, also when you look, for example, at climate change issues. If you want to see how the temperature of oceans evolves over thousands of years, etc. So these are just topics that are still debated, and where heat transfer, the phenomena of heat transfer, is very important. So what we will look into as a homework is this half-space cooling model. That's something we come to in the second part then today, when we look at the example. Good. Let me show those then afterwards. So what I'm quickly going to do is we look at basis functions, quickly recap the finite-element method. And I want to show you that we do have quite a bit of flexibility in the finite-element method. One of the choices that we can do is about the basis functions that we want to use. And so just want to give you very brief examples of how these basis functions could look like, for example, for a finite-element method. And when we do so, it will help us also understanding then where the spectral element method, our last method that we will come to, differs from the finite-element method. So for that, I will quickly show you the whiteboard, and then draw you some of these sketches on the whiteboard. And then in the second part, we come back to the homework example about the half-space cooling. Good. So the first part I want to mention here is on basis functions. And there is quite a bit of choices that we have, actually. So in 1D, what we looked at so far were these tent functions. So in particular, these were linear functions. So we had these tent functions, they looked something like that. We had xa minus 1, xa plus 1. And then we had like these tent function like, which are linear functions. So when we look into the reference element, So we map this to our reference element, which goes between -1 and 1. And then we had these two linear basis functions. We had n1 and n2. And here is xi. There's 1 of xi, 2 of xi. And so we chose to have linear basis functions. So we defined these two linear basis functions, n1 and n2. And so within the reference element, so for the reference element, we chose that our function approximation is linear. So we had two nodal points and two shape functions. So A was 1 to 2. And then we can write this approximation of U as a coefficient UA times NA of xi. That was our function approximation that we did using linear basis functions. And these two linear basis functions, they look like that. So we had n1 of xi, which was this 1/2 1 minus xi, and n2 of xi, which was 1/2 1 plus xi. So these are linear functions. That was our choice, basically. So we don't have to choose just linear functions. If we want to have a better function approximation, we can increase the order, basically. We can use now also, for example, quadratic basis functions. So how would that look like? So let me quickly draw the sketch now for the reference element. So if we would have quadratic basis functions, then we would use polynomials, basically, of the form like P of xi would be A0 plus A1 times xi plus coefficient A2 times xi square. Now we have a quadratic polynomial. So you see on top we had these linear polynomials. If you want, think of the polynomial as being P of xi was A1 times xi plus A0. That was linear above. Now let's choose quadratic polynomials as basis functions. So now we have this quadratic term. And our reference element now has 3 nodal points, not just 2. We still have the 2 endpoints, but now the third nodal point in the middle. And so if we want to plot or draw now these polynomials, we will have 3 nodal functions or 3 shape functions now for that reference element. So the first one will look something like that. Will be 1 at -1 and 0 at the other 2 nodes. Second one, let me see if I can use different colors. Will look something like that. Is 1 in the middle and 0 at the other 2 nodes. And the third one will be like very similar to n1. So now we have n1 of xi, n2 and n3, three nodal functions or three shape functions. So our function approximation now looks like the sum over these three shape functions with these coefficients ua times na of xi. And in this case, we have, for example, when we define this range between -1 and 1 for our reference element, then we have these quadratic polynomials that we can define like this. So we have xi -1 times xi, and 2 will be 1 minus xi square, and 3 will be 1/2 xi plus 1 times xi. So now we would have an increased approximation of the function. Now we would approximate it by quadratic basis functions. So that increases the order of accuracy. And you see how it continues basically. We can now just add, instead of quadratic, cubic polynomials, etc., etc. And that again will lead to an increase of nodal points for each reference element and an increase of the nodal functions or the shape functions that are used. In 2D, let me just draw a sketch for the linear functions to keep it simple. So in 2D, what can we have? For example, triangles.
Professor?
Yeah?
So will we increase the number of nodes while we increase the order of the function? That means if we use the polynomial to describe the function, then the nodes will be more, right?
Say it again?
I'm wondering that if the nodes will be increasing, if the basic functions will be more, will have more orders.
Yes, the number of nodes and the number of basis function that goes together. So if we define quadratic basis function in order to find these coefficients a0, a1, a2 for the polynomial, we need then to have 3 points in order to determine these coefficients. With only 2, with the 2 points at -1 and 1, we wouldn't have enough to constrain these polynomials. So we need a third point, and then they become unique.
Okay.
So what you would do is basically you define these polynomials, let's say quadratic polynomials. Then you have these coefficients a0, a1, a2 that you need to determine now. And so in order to determine these coefficients, we need 3 points. So we define them to be, and for this example, at -1, 0, and 1. But you could also, if you prefer, define the range between 0 and 1 and have an additional node in the middle at 1/2. For example, that's up to you how you want to define the reference element.
So if we have the second order of P, so is it optional to have the 3 nodes, or it have to be 3?
you need 3 nodes to have a solution to the polynomials, because what you want is to have the polynomial determined such that there are 1 on one node and 0 on the other nodes. That is a constraint for which you can then figure out what this A0, A1, A2 coefficients need to be for the polynomial.
Okay.
So we did something similar for the linear shape functions. We defined n1 and n2 here above such that we have n1 being 1 on the left side and 0 on the right side. The same for these polynomials. You want them to have to be 1 on their associated node, basically, and 0 on all the other nodes. And here we have 3 coefficients, so we need 3 points actually to have a unique system for that. But if you change the range, then these coefficients will look different. So for this range, for example, you would find basis functions that would look something like that. 1 minus 3 xi plus 2 xi square for n1. And 2, you don't need to write this down, just to give you an example. And 3 of xi would look something like that, minus xi plus 2 xi square. So you see these coefficients A0, A1, A2 depend on what the range is for your reference element. So if we choose our reference element to be between 0 and 1, then we would have a different set of nodal shape functions because these coefficients would look different. But again, this is basically determined by having 1 nodal point at 1 and the others 2 need to be 0. That's the constraint, how we find these coefficients. Is that kind of clear?
Yes, it is. Thank you,
Okay.
Professor.
Good. Let's look at 2D examples, for example, triangles. So again, if you look in the physical domain, the triangle might be stretched, skewed, something, whatever. What we are interested are now the mapping to a regular triangle. So then our triangle will be defined, for example, between 0 and 1 range. So we had point 0, 0, point at 1, 0, and here at 0, 1. And then we would have this regular triangle defined as our reference triangle. And so if we choose linear polynomials in 2D, for this triangle, we would see that the polynomial would look something like, oops, not just xi. Let's say this is xi direction, but then the second direction would be eta. So then we have coefficients A0 plus A1 times xi plus A2 times eta. So that would be a linear polynomial. And then again, we're going to define these polynomials to be 1 on one nodal point and 0 on all the others. that determines then the coefficient. And so that's how we set up then the system of nodal functions or shape functions. If you want, we could have quads, something that is again kind of distorted in a physical space. It's going to be mapped to a reference, a regular reference element, again with psi and eta direction. And then here we can again define, for example, between 0 and 1. And for, like here, polynomials would look like something like that, where we have a0 plus a1 times psi plus a2 times eta plus a3 times psi times eta. So now we would have these four coefficients, a0, a1, a2, a3. We would need to determine for this reference element. Again, such that one polynomial is 1 on one node and 0 on all the others. And obviously you can also use then quadratic polynomials for these elements. But this is how you would extend it. For example, from 1D to 2D. And then you see how it continues for 3D, etc. And there's a lot of different possibilities. That we have with these basis functions. Now, often the finite element method uses low order polynomials, linear, maybe quadratic polynomials. Those are the most popular approaches for a finite element method. And then also we saw also the mapping here, this psi of x. The mapping, we also chose it to be linear. So the mapping had the same linear shape functions, if you want. So it's a linear mapping plus a linear basis function. So mapping and basis functions were of the same order. In principle, we can have the freedom of choosing different order for the mapping and a different order for the basis functions, where we do the function approximation. So often the mapping is, let's say, linear or maybe quadratic, where then the basis function can be a higher order, can be cubic, etc., if you want. So there is kind of a freedom of choosing what the order of the mapping should be, and the mapping determines pretty much what geometry will be built upon for the reference element. And the basis determines how good the function approximation will be within that reference. So when we come to the spectral element method, we see that we separate these two things. We will choose linear mapping for basically determining the geometry and the mapping to the reference element, but then use a higher order polynomial for the function approximation within the reference element. So just be aware that we do have these two separate parts that we can choose differently the way we want, basically. We started by having both as linear functions, mapping and basis, but you can think of having the freedom of choosing different orders for these as well. But the most simple, most common approach for a finite element method is to use a linear mapping function and linear basis function. So mapping and basis functions are the same then. That's just by simplicity, introducing the method. But be aware that you do have the freedom of going to higher order basis functions, for example, or also the mapping. Good, that's about the basis functions. Then about this mesh structures and unstructured meshes. That's
Professor?
Yeah?
I think Tariq waiting for your confirmation.
Oh, right. Great, thanks. Let's see if it works, adding him.
Hello,
hi, Tariq, are you in?
yes, Professor. Sorry for being late. I just
good.
forgot about the class.
Anyway, we have it recorded, so you can look at the beginning as well. So the second quick point I wanted to make is about unstructured meshes. It's mostly about this mapping from local index back to global index, where this actually comes into play. Or we had, for example, in our example, we used more a regular approach where we had our domain discretized in a different number of elements. Then we had element 1, element 2, element 3, etc., all ordered. That doesn't need to be the case. If you want also on a global level, the points here were just labeled from 1, 2, 3, 4, etc. So they were all ordered, which because of the 1D example, etc., just happens to be very easy to do actually. But when you go to 2D, especially 3D, and you want to accommodate like these complex geometries, the mesh becomes unstructured. You don't have like a simple ordering anymore that your mesh obeys to. So it's called then an unstructured mesh. But you see the ordering is basically captured by our location matrix. So if we think of the global node A index being our location matrix stored in that one, where we had the local node and the element, which was this indexing between local and global. So even if the mesh is unstructured, we still have the same approach. We construct this location matrix. Location matrix will look a bit different because now we do have different ordering of the numbers. But at the end, we still use that kind of approach. We still use a location matrix, which brings us from a local node to a global node point. So it's very easy for the finite element to accommodate structured or unstructured meshes. There's very little difference in how we need to accommodate that. So like in this example where we had this structured location matrix, it looked something like that. We had nodal point 1 and nodal point 2. And then the ordering went something like that. 1, 2, 2, 3, 3, 4, etc. Till n and 0. That 0 was because of the boundary condition. But you see, the example was structured. It was just increasing, basically. But obviously, you can also easily make it unstructured. And if you would switch here the nodal points. So if you go from 1 to 3, 2, 5, 4. Now we do have different global indexes on these nodes. And accordingly, the location matrix will look like a different as well. But again, it's pretty simple. So we have our two local nodes, xi1, xi2. Let's say this is element 1. We can also play with the element number as much as we want. Say this is element 3, 2, and 4. Then we had element 1. Xi1 was 1. Xi2 was 3. That's the global index. Then we had element 2. There will be 2 and 5. Element 3 had 3 and 2. And element 4 had 5 and 4. For example, this would be element 2. But at the end, the algorithm doesn't change, actually. You just keep track of what this indexing is between local and global level, the location matrix. And then you can easily accommodate unstructured meshes in a finite element approach. So there is no magic in that. You see, for a finite difference method, it becomes much more trickier. When we had these fi minus 1 plus fi plus 1 by 2 delta x, for example, finite difference stencils in principle need a regular mesh, a regular indexing. Otherwise, you have to work around this formula, for example, to make it correct. So you would also need to have some sort of an array which keeps track of the indexes. So this is based on irregular meshes. Well, here this is unstructured meshes. So that's one of the reasons why the finite element method is much more flexible than a finite difference approach. You're much more flexible in terms of the mesh that you have now. the ordering, the indexing on the mesh. It doesn't matter. We just need to keep track of it with this location matrix, which maps from a local to global level. So that's pretty obvious. In terms of computational benefits, the regular meshes are faster. If you have a way of finding the position based on the index with a direct formula, that you know that xj is equal to j times delta x, that's faster than finding the position in a finite element grid. Here the xj position that will be in depending on the local node and the element. I don't know how to write that, but you have to involve more of memory retrieves in order to find, for example, a location. You need first to find its index, and then looking up the index in a position table where you can read out the position of the point.
Professor?
Yeah?
I'm now really confused because I don't know what's the real meaning of the table, like the epsilon 1 and epsilon 2. Because sometimes I think that it's the number of the element, but
Right.
you said the last one should be 0. Why is 0? Because it's just the number of the element.
It would
it's not
be
the degree of freedom, right?
It is the same in our case. So you see, we had this boundary imposed. Oops. The boundary condition imposed on the last node. So there was no degree of freedom on that last node.
Yeah.
So here, if we would want to do the same, then again here, this point would be 0 because of the boundary condition. And the number of shape functions would be the same like the number of elements. And we have this linear setup. Again, that's the confusion with the boundary condition. If there would be no boundary condition, then yes, this would just be n+1 node. And for each node, we have a corresponding shape function.
Yes.
And a corresponding degree of freedom. So these dA, NA. And now we have the sum over A to N. And the question is, what is N? Is it the number of elements or the number of nodal points? And in a general case, it's the same like the number of nodal points you have. For each node, you have a degree of freedom where your solution can be free to be whatever it is.
So,
but because of the boundary condition, we have this, in our example, we had this last nodal point fixed. We fix what the temperature field, for example, needs to be in that last point. That takes away that degree of freedom. And so then n was the number of elements. So that's the confusing part. So here the location matrix, in principle, it would just, in general as well, just continue with n+1. Or like in this example here, global index 4 at the end. But then the way we set up the function expansion and the number of shape functions to account for the boundary condition, we put this to 0. Otherwise, we need to fix the degree of freedom later on.
So can I say that for the unstructured meshes, the last point, the freedom of degree for the last point is 4? If
No,
there is no boundary condition.
For the location matrix, yes, then the index just points to 4, yes.
Okay.
But so this location matrix just gives you the index for that point, for that nodal point. And it is related to this nodal shape function that we have for that particular node. And so if there is no degree of freedom, then we don't need to have that nodal shape function to keep track for the indexing. That's why we were able just to send it to 0.
Okay.
Yeah, that's the confusing part with the boundary conditions. But look up the example again, how we choose our functions to be, test function and the function expansion, the temperature field of u, and then what the actual degrees of freedoms are that we invert for. So when we have this d vector is 1 over the stiffness times the force vector. So these are these coefficients d1 to dA. So these are only the degrees of freedom that we are free to choose, basically. But the boundary condition fixes our last point here. So we don't want to have that last point shown up in that linear system of equation. The linear system of equation is really just to determine the unknowns.
So maybe
probably I'm just making it more complicated.
Maybe we can say that the freedom, the degree of freedom for the last element is d4, not the number 4. Then it's understandable. Okay. Yeah, I guess it's really confused.
Well, we can have, if you want, on the global point, d1, d2, d3, d4, d5. Or on the unstructured, it would be d1, d3, d2, d5, d4. Those will be our degrees of freedom associated with each node.
Okay.
And if we don't have the boundary condition, then yes, that is an unknown, that is a degree of freedom, which comes in here. So then we have here d1 to d5 that we need to solve for. Now with the boundary condition is d5, or in this case d4, there are no more degree of freedom because we fixed the field in these nodes. So the unknowns would be only d1 to d4 for the structured, or we would have d1, d2, d3, and d5. Those would be the unknown. in the unstructured. And then we want to have this corresponding stiffness matrix and force vector set up for these unknowns. Think about it. Next time we also do an example without boundary condition. Think about what would happen if we also would have a Dirichlet boundary on this side. So instead of only having a Dirichlet boundary on the right side, just play around with it and see what would happen when we have it on both sides. How would this look like? And how would the system here, the linear system of equations look like? And the function expansion and our u of x equal to what? That's a good exercise, actually. Yeah. Trying to figure out these effects from a boundary condition. Good. I'm making a mess here now. Let's come back to the example. Okay. Good. I think for the example, I can show you the slides again. Good. Let me stop sharing this one. And let's come back to the heat transfer now. For that, I can show you the slides. So let's continue with this one. So, for the example, what we look at is now the non-steady-state diffusion equation. And you see on top the strong form of the non-steady-state diffusion. So this is the 1D heat equation if we ignore convection. And then we end up with this non-steady-state diffusion equation. Yeah, maybe let me put this down as well here in the whiteboard, just to quickly give you the idea of the equation. So what we're interested in is heat transfer. And heat transfer is based on the conservation of energy. And if you remember, assuming Fourier's law, about the temperature gradient. So we can write the 1D heat equation as following, and this assumes that we ignore convection. So in absence of convection effects. It's really a diffusion equation that we're looking at. So we have rho density times specific heat, and now there is this temperature dependence, the derivative of the temperature field with respect to time is equal to this diffusive term. We have kappa, the conductivity of the material, plus F, a source. And here, just to remind you, T is now temperature. Which depends on position and time. And that's now the difference to the steady state diffusion equation, where temperature was always only a function of position of x, but not of time. Now we look at the non-steady state, so temperature can evolve with time. And then CV, that's specific heat. Kappa, that was conductivity. And then F, that's either a heat source or a heat sink. And so what we want to come to is basically the half-space cooling model. And for that, it's convenient to look first at the example where we have this long rod. Again, you can think of a long rod. On one side, we have a constant heat flux. Let's say Q0. And on the other opposite side, we have a cooling temperature. Let's say TL. And we can have here an initial temperature profile, which will be T0 fix. So the boundary conditions can then be written as having the temperature at position L fixed to temperature TL. Who knows what kind of boundary condition this is? Is it Dirichlet or Neumann boundary?
Directly.
Yeah, this is Dirichlet. Now we come to the Neumann boundary at position 0. So there we look at the derivative, which has to be equal to this constant heat flux. And then the initial condition, that will be Tx at time 0 is this T0 profile. So these are the boundary conditions and initial conditions for the problem. So what is the finite element approach? So we're going to apply, it's these 4 steps basically. Just let me quickly recap these steps. So first one, look at the weak form. Second step would be the local contribution. Local element contributions. Third step would be the assembly. And the fourth step, what is missing?
Inversion.
Yeah, let's assume this belongs to the assembly part.
Then we find the solution using the D vector.
Right. But what is new in this example compared to the steady state?
Time dependence.
The time dependence. So we do have the time scheme. Let's say this is our 4th step. Weak form, element contribution, assembly, that's all the same like in the steady state. The new step is actually the time scheme that we need to have in order to solve this. For the homework, this is basically the initial problem set, trying to solve this example. 1D heat equation with these boundary conditions. And I'll show you like what time scheme we're going to use for that in a second for the example slides. Then the second problem that we want to come to is the actual half-space cooling model. And is pretty much related to this this initial example that we had. So the half-space cooling is for an oceanic lithosphere. Well, we assume that we start with a uniformly hot plate, or if you want, half space. Slowly cooling down then. So now let me plot you a vertical profile. What we would have here, X is in vertical direction, and we have time t0, a uniformly hot plate, which means the plate is at the same temperature like the mantle. Everything has mantle temperature, so try to plot you the profile, the temperature profile would be something like that, where this is at the mantle temperature. So think of going down, vertically down, and look at the temperature profile. And so we start with a time t0 with just a uniformly hot plate. And then as time evolves, where's the cooling happening?
Decreasing temperature.
At 0?
Carly, I couldn't hear you, but yes, at 0, it's the ocean. The ocean cools off the plate. So here on top, this would be cooled down to a temperature T0, which would basically be the temperature of the ocean water. And you see the ocean cooling is trying to keep this top always at temperature 0, T0. Let's say it's 4 degrees. So we have then a cooling temperature on this side, and this initially, like this constant heat flux on the other side, which comes from the mantle. So the profile would look, after some time, would look something like that. It goes down to Tm, to the mantle temperature. Let's say this would be 10 million years. Here we still have this T0, but now we have this kind of diffusion, heat diffusion that we see. So if we want to plot an isotherm, let's say at 1,000 degrees, then that would be maybe around here. This would be 1,000 degrees Celsius. And you see it keeps going. Now we have more cooling. And let's say after 100 million years, the same temperature, the same isotherm will be now at a different depth. So if we plot now the H versus the depth profile, we would have now an isotherm that looks something like this. So if we would have here 0, in this case the H, and now we plot temperature. Then this isotherm would look something like that. At constant temperature. And so H also depends on the distance from the ridge, because the plate moves, and if we assume the plate moves with a constant velocity, then we can easily calculate what the distance is after 10 million years, 100 million years, etc. So this half-space cooling model, one of the assumptions that goes into it is that the diffusion in vertical direction dominates compared to diffusion in a horizontal direction. It's really the temperature gradient in vertical direction is much more important than the temperature gradient on horizontal. So we can ignore this horizontal effect. And so it becomes really just a 1D problem then. The whole temperature dependence is now a 1D problem. And what it comes to is the diffusion equation. Simplified for seafloor spreading. Which assumes that lateral diffusion is much smaller than vertical. So what we end up with is an equation that looks something like that, where we have rho CV times, now this would be, let's say, T hat, with this diffusion term, where this T hat is a non-dimensionalized temperature, which would be temperature minus the mantle temperature divided by the difference between the cooling temperature and the mantle temperature. So this is a non-dimensional temperature field then. T0, that's the surface temperature. And just by simplicity, let's assume the surface is at 0 degrees Celsius. And Tm would be the mantle temperature, or the initial temperature. Which, like, typical value for mantle is around 1000 degrees Celsius or 1300 degrees Celsius. So that would be the heat transfer equation, or the heat diffusion equation for the half-space cooling model. And the boundary conditions in this case, we have the temperature at 0 is kept at this surface temperature. That's the constant cooling temperature. Then the temperature, if x would go to infinity, is kept at the mantle temperature. And then the initial profile is at the initial mantle temperature. So the problem is related to this initial problem that we set up. Just put the boundary condition at slightly different place, but then we have the half-space cooling model set up. So let's go through the slides quickly, 2 minutes, and then we are done for today. So good? Oops, let me share the slides. And then I hope you understand what the problem set will be for the non-steady state diffusion equation. So on top you see the equation, non-steady state diffusion. Good, with the boundary condition and the initial condition. And so we're going to solve this with the finite element approach, put this into the weak form. And again, look at the boundary condition. We also have a Dirichlet boundary. So that makes now the function expansion again, like we had in the steady state example. So W is the test function, and here now T, that will be the temperature field. We put this again into this matrix form, and we will see something like that. And here new is that we have this capacity matrix also called. So on the left-hand side, this term with rho times the specific heat, etc. That will become the capacity matrix times the time derivative of our coefficients, of our unknowns. Then you can take over the stiffness matrix equals to the force. So these will be like the contributions for the capacity matrix on top, this MAB contributions, the stiffness contribution and the forcing contribution. So that will be on a global level. And then we're going to map this again to our reference. So let's look at the local level, how this would look like. Again, we use linear shape functions. And then you can write down, for example, what the capacity matrix contribution looks like on a local level. So this will be capacity, stiffness is the same like for the steady state. And then the forcing looks again very similar to what we had for the steady state. Then you have the assembly stage. Again, is the same thing with the location matrix that you would set up. And now comes the time scheme, and the way we're going to solve the time stepping here is with this so-called predictor corrector scheme or algorithm. And we're going to start using this one now, because when we come to the spectral element method also, we're going to use this sort of predictor corrector scheme. So it's one particular choice for a time stepping. But you see how you would start with a predicting step. Then you update what your increment should be. So you need to solve this right-hand side term. You're going to solve what the velocity or the time derivative of the coefficient d are. And then you can do this corrector step. Once you have this correction solved, you update now the position at dn and the time derivative, dn plus 1. And then you loop over that. So you see these predictor corrector schemes, they are related, for example, to forward differences, backward differences, or this midpoint rule, for example. That's the one that we want to use. So this alpha is a parameter for this algorithm. And that's something we can choose. In this case, we choose it to be 1/2. So we can now update the temperature dependence of our coefficient. So the scheme is very simple actually to implement. There's not much different than the finite difference schemes that we used also for the time dependence, time discretization. Good. So we can solve this, for example, with a simple harmonic function. That's the initial problem. That should look something like that when we have it right. And then we go to this half-space cooling, where we can figure out a bit what the transformation should be to map the right boundaries at the right location. And then this should become something like that. So now we can start playing around with the number of elements. Like here, left side 10 elements, right side 20 elements. And you have this temperature profile that you should see evolve over time now. So you should see how the cooling basically propagates downwards of the plate, leading to this thickening of the plate. And here it's just a bit confusing with the way it's plotted. But maybe easiest if you think of having this such that x goes in vertical direction, for example. No good. That's the homework 6 example then that we're going to attack. So once you figured out the steady state, you can use a lot of it for this example. The new ingredients in this example will be the time scheme plus this capacity matrix. And then we can solve this half-space cooling model as the goal for this homework. Do you have some questions for that? Is it clear? I will put again like all these slides you will have to double check the template code. I have a template code in MATLAB for this example. I see if Python will do it as well. I'm not sure if it's fast enough, but I'll check and then provide you the Python template in case as well. Good, and then with that example, we are basically finishing up the finite element method. The last, second and last example for the finite element, and then we come now to the spectral element approach.
Professor, for this finite element, we don't consider about the stable condition or not. So it's always stable, right?
Here, the boundary conditions are, well, yes, it's a kind of simpler, especially the like the free surface boundary. When we come to the wave equation, you will see it's very simple because that term just falls out, becomes zero. So we don't need to do much there. If we impose a Dirichlet boundary, that's you see it becomes part of the fixing of the degree of freedom at that boundary. So here for the finite element, the boundaries are simple to implement. Plus the basis functions are local basis functions. So they have local support. So the whole method is a local method, can be easily parallelized. And we don't have issues with assuming to have periodic boundaries, like when we use a Fourier transform, etc. So in that sense, is an easier method to implement your boundary conditions. Good. So I would say we see each other next Thursday, and then just discuss the steady state example that I hope you will hand in by Wednesday, so we can look at it on Thursday and go through it. And probably it helps just making sure that you understood the problem, and then this non-steady state heat diffusion becomes much simpler. Is it good? Good with everyone?
Good.
Okay, good. Then we'll see each other next Thursday.
Thank you, Professor.
Thank you,
See you.
Professor.
Thank you.
Good. Have a good Sunday. Bye, everyone.
Bye.